In this video, I am going to analyze and solve a problem on moment of force, also known as torque. The given problem is a uniform plank of length L equals 6 meters and mass capital M of 90 kilograms rests on two supports separated by distance d equals 1.5 meters and equidistant from the center of the plank. A boy wants to stand on the right-hand end of the plank. If the plank is to remain at rest, how massive can the boy be? In solving this problem, we are going to apply two physics concepts. Okay, these are the two conditions, translational and rotational equilibrium. Okay, the first one is that the summation of all forces, external forces, acting on a body must be equal to zero. The second one is for all external moments of force, also known as torque, summation of all torques must be equal to zero. So summation of forces equals zero also means that acceleration, linear acceleration, must be equal to zero. And for summation of torques equals zero, it means also that the rotational acceleration must be equal to zero. So if these two conditions for equilibrium are satisfied, then we say that the body neither moves linearly or rotationally. Alright, so this is how we interpret the problem situation. You have here the sketch, how we visualize what is going on. Alright, first, let's identify what are the given quantities. So we have the length of the plank. This is the horizontal plank. Alright, and the length of that plank is given as 6 meters. Okay, now we assume that the plank has a uniform density, all right, which means that its center of gravity or center of mass is exactly at the geometric center, and that is denoted by the symbol C. Right. Now, uh, one of the methods that we are going to apply in this uh, problem is to consider the what we call center of gravity of a system. Okay, we define the system here as composed of the lever as well as the buoy, and the buoy and the plank, okay, their common center of gravity is represented here as CG. Okay, that's the center of gravity of the plank buoy system. Now, um, we also want to know, or we have here a representation of the distance from the geometric center of the plank, okay, to the support S, okay, and we label it as X sub S. That actually is going to be considered as the lever arm of the support S. And according to our drawing, since the two supports are separated by a distance of 1.5 meters, denoted by small letter d, okay, it follows that half of that, okay, which corresponds to the value of x sub s. Okay, so what is half of 1.5 meters? It is 0.75 meter. Okay, at this early, we're identifying the important quantities that we will be needing for our computation later on. All right. Also, we have here labeled the distance of the center of gravity of the system, okay, CG, or it could also mean the distance of the support from the rightmost end of the plank. And according to our label here, it is equal to L over 2 minus D over 2. Since L is 6 meters, L over 2 therefore is 3 meters, while D over 2 means half of 1.5, and that gives us uh, 3 meters minus 0.75, so that's equal to 2.25 meters. We'll be needing that measurement also in our computation later. But at this point, as in any other problem solving involving static equilibrium, okay, we first identify what are the forces acting on the plank. It is the plank that we are considering as the body, all right, acted upon by external forces. So, we have, of course, the weight of the plank, or the pull of gravity, denoted by this symbol, arrow, pointing downward. Okay, why is the force of gravity, okay, exactly at the center of mass? Because we can say that the concentration of the weight of the plank, all right, may be considered to be passing through the center of mass. Center of mass is just the same as center of gravity. All right. So that is the downward force exerted on the plank. There's another downward force exerted on the plank, and that is, of course, the pull of gravity on the buoy. Okay, pull of gravity on the buoy. But since the buoy is standing, okay, on this part of the plank, he is also exerting the same amount of force equal to his weight. And that force that is exerted on the plank is directed downward. All right, so these are the two downward forces acting on the plank. All right, why do you think the plank should stay at rest? In other words, it is in state of translational equilibrium. All right, when a body is in translational equilibrium, we say that the summation of all external forces must be equal to 0. All right. Since there are two forces acting on the plank downwards, there must be what we call upward forces also exerting on the, or exerted on the plank. And where are these upward forces be coming from? Of course, as you can see, the plank is supported by these two triangular supports. So these triangular supports will each be exerting an upward force. All right. The left support is exerting upward force, denoted by the red arrow, that's upward. And similarly, the other support, the one on the right, labeled S, is also exerting that upward force on the plank. And if we are going to add, all right, if you're going to add all these forces, the upward forces, the downward forces, they will all add up to 0. And we say that the body, which is the plank, should stay in translational equilibrium. That's just another way of stating Newton's first law of motion, which is F net must be equal to 0. All right. Now, We also assume that the two supports are what we call this symmetrically positioned, all right, on the plank or to support the plank. Okay, in other words, uh, each support has the same distance from one end, from the left end of the plank, as well as to the right end. Okay, so supposing there is no boy yet in the picture, all right, let's assume that we are only talking about the plank and the supports. With that condition, we say that the plank is in a perfect static equilibrium. There will be no F net or no summation of forces. They will all add up to zero. And one thing more, we say that the system, the plank, is considered in rotational equilibrium. What do you mean by rotational equilibrium? Earlier, okay, we mentioned that, which simply means that um, the body is not going to undergo any rotation. And we know that rotation or rotational motion of a body is determined or caused by what we call torque. If there is torque, okay, an external torque is applied on a body, then there is a possibility for the body to undergo rotation. Okay? Now, uh, another point that we have to consider, if you notice the four forces acting on the plank, okay, the upward and the downward forces, they are not concurrent forces. Okay, they are not concurrent. In other words, when you are going to determine their lines of action, they will not intersect at a common point. That is what we mean by concurrent. No, they are not concurrent. They may be coplanar. Coplanar means that all the forces here are assumed to be lying on the same plane. All right. So as shown by our compass here, we say that we are only talking about two-dimensional. What do you call this? Uh, the four forces are considered only two-dimensional. Okay. There is no what we call a third dimension here. So hence the assumption that the four forces must be coplanar. Okay. Being coplanar simply means that all the forces only have the same, they are lying on the same plane, involving only the x and the y coordinates. All right. There is no z-axis involved here. All right. So back to my uh, what I was trying to say. If the forces are not concurrent, there is a possibility. All right. There is a possibility for them to what we call undergo rotation. All right. There is a possibility. They may be equal, okay, to zero, but the probability for the torque not to be equal to zero is there, no, in the situation. All right. So the concept, the physics concept that is applied in this problem situation, as a matter of fact, is really about rotational equilibrium. All right. And the concept associated to rotational equilibrium is the fact that uh, we will be considering the summation of torque to be equal to zero. Okay, it's also the same as saying that there will be no rotational or angular rotation. All right. Now, uh, these forces, all right, if the boy is not yet there in the picture, these forces, okay, to check if there is any force Okay, if there is any force, supposing the boy is not yet there, so we take away first the weight or the force exerted by the boy on the plank. So if there are only three forces acting on the plank, okay, the downward force of gravity and the two upward forces of the two supports, okay, how would you know? How would you know if the plank will stay in rotational equilibrium? All right. From experience, we know that if the plank is resting on the two supports with its center of mass exactly here, its geometric center, and there are two supports, all right? Uh, there are two upward forces trying to compensate for the force of gravity, then we are assured that the body is indeed in state of translational equilibrium. And supposing this uh, upward force coming from the left support, okay, will cause a torque, okay, if it has the ability to make the plank rotate about the center of mass of the plank, okay, in a clockwise manner, okay, how do we know that it's going to be clockwise? Because if this is our assumed axis of rotation, point C, then okay, this particular force will somehow rotate the body or cause the body to rotate in a clockwise direction. And for as long as another force upward, okay, coming from the right support S, okay, will also produce an equal but opposite torque on the plank, then there's no problem. Okay, if we add the two torques, they will be numerically equal, meaning the summation of torque will just be equal to 0. All right? That is if the boy is not yet in the picture. Now, supposing we are going to imagine that the boy, all right, the boy starts to walk, all right, starting from here at the center of the plank, and he intends to walk towards the right end of the plank. All right? Okay. If the boy has a particular mass, then um, our problem would then be how far can he go, okay, beyond the support S? How far can he go beyond the support S to prevent the plank from tilting? Okay? Is there a chance for the plank not to tilt if the boy reaches the far end, the right end of the plank? Okay, but that is not the question raised in the problem. Okay, the problem is actually to determine what is the maximum amount of mass of any person. Okay, what is the mass of a person who will attempt to move beyond the right support, all right, beyond the right support and up to the end of the plank, all right, up to the end of the plank without causing the plank to tilt. Okay, what is that maximum mass of that person so that the plank will just be on the verge of tilting, all right? The plank will tilt, okay, if the force of gravity exerted by the person on the plank will cause the plank to rotate clockwise. At that instant, all right, at that instant, assuming that the person is able to stay up to the end of the plank, all right, but he is on the verge of making the plank tilt, then we are saying that at that instant, the force coming from the left support, this upward force, is also approaching 0. Okay, can you follow? If this upward force of the left support is 0, then there will only be one support. Okay, just the right triangular support will be balancing the plank as well as the buoy. Okay, do you see that? And uh, if the center of gravity of the system, meaning the combination of the plank and the buoy, okay, they are considered the system. If their combined center of gravity, which we label here as CG, is exactly, all right, is exactly where the force of the right support is located, okay, if the center of gravity of the system is exactly at this point, then we say that the system, the buoy and the plank, will still remain in equilibrium, or they will not undergo any rotation. In other words, they will both be balanced, okay, if the support is exactly at the center of gravity of the system. Okay? Now, so that is essentially what we are going to consider, that principle of determining the location of the center of gravity of the system. All right? We call it the center of mass of two composite bodies which make up the system. As is now, we actually know where the center of gravity of the system is. All right? Because we know how far the right support is from, say, for example, from the center of mass of the lever, I mean of the plank. We know what this distance is. In fact, we label it as x of s. Okay, that x of s can be assumed to be equal to the location of the center of gravity of the system. And that actually is equal to d over 2, okay, which is 0.75 meters. So there's no problem right now about the exact location of the center of gravity of the system. All right? But knowing that center of gravity, okay, we are able to determine what the mass of the buoy is. All right? And that is what we are going to follow in our first method. The first method for our solution will be considering that concept. Okay? That concept of center of mass or center of gravity of a system. So, we are going to I'm going to explain to you the formula involved that will be coming in the next slide. All right, so here we are again. Uh, our task is to determine the mass of the buoy, the maximum value of the mass of the buoy, uh, so that upon reaching the end of the plank, he is on the verge of making the plank tilt. Okay? Since we know what the center of gravity of the system, all right, we can consider that as our uh, formula in determining the mass m, small m. All right, here is the formula. Okay, the formula actually is based also on the principle of torque. Okay, but first we have to assume that the geometric center of the lever is our reference. Right? We will let point C be equal to x equals 0. All right? So that's our reference. And it's like determining the different, what we call torques. Okay? The different torques uh, based on that arbitrarily chosen axis of rotation. Okay? So arbitrarily, all right, we choose center C as our axis of rotation. And then analyze what are the different torques, okay, that we can visualize here if the axis of rotation is at point C. Now, the force exerted by the, what do you call this, by the support S, okay, which is pushing the plank upward, is exactly at this point of the center of gravity of the system, okay, and it has a corresponding lever arm which we earlier identified as X sub S, okay. The lever arm, meaning the distance from the chosen axis of rotation up to the line of action of the upward force coming from the support, okay. So we actually labeled that in the formula, it's labeled as X sub CG. X sub CG is the lever arm, okay, that we consider if our axis of rotation is the center of mass of the plank, labeled C. Okay, if we multiply that by the total mass of the system, meaning capital M plus M, then we are determining, practically we are determining the amount of torque, okay, the amount of torque corresponding to the upward force that will cause, okay, that will cause the system, or specifically the plank, to rotate in a counterclockwise manner if this is our axis of rotation. Okay, can you follow? If the upward force is exerted and then there is a lever arm, that means it produces a counterclockwise torque, and that's exactly the meaning of xcg when multiplied to the combined mass, capital M plus M. All right? So, what's on the right side of the equation? The right side of the equation also refers to the two possible torques. The first one is supposed to be the torque that will be produced, okay, by the force of gravity, all right, the force of gravity on the plank, meaning the weight of the plank, which is directed downward. So you see, that's opposite to the force exerted by the support S, all right, and that what do you call this? That weight or that pull of gravity happens to be exactly the line of action of that weight or force of gravity is exactly where our assumed axis of rotation is. In short, it has no lever arm, all right? The lever arm is 0, all right? That is the meaning of capital M times 0. That is supposedly the torque coming from or produced by the force of gravity of the plank. But since we have chosen point C as our axis of rotation, then it follows that such force of gravity will not cause any torque on the system. All right? Then how about the other one, M quantity L over 2? This pertains to the torque, all right? The torque that is exerted by the force of the person or of the boy on the plank, all right? Small m is the mass of the boy multiplied by the acceleration due to gravity, then we are talking about his weight, which happens to be also equal to his force on the plank. All right? Then, uh, since we are only isolating the xcg, all right, xcg, then we transpose the what do you call this? The masses, capital M plus M, and this is the working equation, okay, that we need for applying this method 1. So essentially, or basically, what we are just applying in this problem is the principle of center of gravity or center of mass of a system. Okay? And further, what do you call this? Derivation of the formula. Okay? So if we derive the formula, it will come out this way. So we are trying to isolate small m, All right. Since big M times 0 is already 0, so we just exclude that, no? And we are left with this part, okay, M quantity L over 2, as well as M plus M. But we substitute, all right? We have substituted earlier our X sub CG in terms of XS, all right? X sub S. That's why our formula will redound to uh, exactly the formula that we need, no? To determine the mass M. Okay, and it's going to be shown in the next slide. Okay, before we proceed, let's look at again the formula for determining the mass of the boy, small m. Okay, so earlier I gave you the formula for uh, the center of gravity, xcg, which is equal to the mass of the lever or the plank, all right, multiplied by 0 since its lever arm is 0 plus, okay, mass of the boy multiplied by L over 2. Why L over 2? It is because the boy, which is standing at the far end of the right side of the plank, has a lever arm which is equal to half of the length of the plank. All right. So that is the meaning of m, small m, multiplied by L over 2. L over 2 being the lever arm that you need to multiply to the mass of the boy. Okay. I wasn't able to clarify that earlier. So as we proceed, uh, also earlier I said that our x sub cg, okay, is just equal to uh, x sub s, all right? And x sub s is denoted by d divided by 2. Okay, so in other words, we can continue determining the mass of the boy, small m, okay, in terms of the quantities big M, the length of the plank, and the separation distance d of the two supports. Okay, so it becomes now like this. Okay, since there's over 2 on the left side location, so on the right side, that can just be cancelled. And what we have is, if we multiply small m, okay, small m by the length of the plank, okay, L, capital L, that becomes ml. And then equate that to the product of capital M plus M, okay, and the distance d. So it's just like we cross multiply, okay, the variables. But what we need really is an expression that has the small m isolated, no, from this equation. And if you do more algebra to derive that small m, you'll come up with this equation in determining the mass of the boy, small m. So it's just equal to big M, quantity, distance d over L minus d. All right? So in using this formula, you first have to determine the difference between the length, capital L, minus the distance d. And then whatever that value is, okay, you will divide the distance d by that value before multiplying the big mass or the big M mass of the lever. Something like that. No? So plugging in the data or the quantities to this formula, we have 90 kilograms, and then we will be subtracting first the length, which is 6 meters minus 1.5 meters, so that's about what, 4.5 meters, and then that 4.5 meters becomes the what you call the denominator for this fraction. 1.5 divided by 1.5 meter divided by 4.5, and whatever comes out, you will multiply it to the mass 90 kilogram, and eventually you will get the mass of the boy, small m, equals 30 kilograms, right? So you need to do some careful derivation, okay, starting from this equation until we get the small m isolated. So that requires a little but careful, what we call this, algebraic manipulation. And I leave that to you, no? And the mass m that we get here is 30 kilograms. All right. You can check this, okay? You can check this value of the mass small m by having another uh, choice for the axis of rotation, because earlier, okay, we agreed that, or I told you that the arbitrarily chosen axis of rotation is the center, the geometric center of the Planck, okay, exactly at point C, right? Now, just to convince yourself that the choice of the axis of rotation is actually arbitrary, okay, meaning it doesn't matter which point you're going to consider as your axis of rotation. All right, you may do that and check if the value of the mass small m will come out to be 30 kilograms. Because the second method that I'm going to discuss in a little while requires a direct, okay, application of the principle of torque. Okay. The second method or process that we're going to apply is application of the principle of torque. All right. So we first determine the important forces acting on the Planck, and one of them, of course, is the force of gravity exerted on the boy. Okay, that's the force exerted by the boy also on the Planck. And then we also have the force of gravity exerted on the Planck passing through the geometric center denoted by letter C, right? Uh, we will let the axis of rotation be at the support S, okay? So only two forces uh, acting on the Planck will be considered because, okay, we are assuming that the boy is at the far end of the Planck and that he is on the verge of making the Planck tilt, okay? At which point, the force exerted by the other support, the one on the left, okay, the upward force that we earlier identified will no longer produce any torque, okay, because the moment the boy starts to make the Planck tilt, that would mean that this left support will no longer be in contact, okay, will no longer be in contact with the Planck, and so therefore, if that force approaches zero, okay, we only have the two downward forces acting on the Planck, okay, and that these are the forces uh, represented by the red arrow as well as the black arrow. Now, these two forces will produce their own moment of force or torque, and this the principle of torque, summation of torque being equal to zero, will actually just be applied to these two forces. Okay? Instead of saying that the summation of torque is equal to zero, we just say uh, counterclockwise torque is just equal to clockwise torque. Now, which forces will cause the counterclockwise torque and which force will cause the clockwise torque? Okay. As you can see, if the axis of rotation is exactly at this point S, which also is the center of gravity of the system, okay? This particular force of gravity, okay, the red arrow, will produce a counterclockwise torque. Okay? It will make the plank rotate, okay, about that axis of rotation in a counterclockwise direction. And to determine that torque, we just multiply the mass of the plank, which is 90 kilograms, supposedly multiply it by the acceleration due to gravity. All right? But since we are just dealing with or looking for the mass m of the boy, there is no need to include the acceleration due to gravity because anyway, uh, even if you're going to include that here, okay, on this left side of the equation, we will also be including the acceleration due to gravity on the right side. And that will just be canceled out. Okay? So there's no need to include the acceleration due to gravity for this equation because we are just looking for small m, which is the mass of the boy. All right. Now, 0.75 meter is the distance from the line of action of this force, okay, at the center C, okay, uh, up to the axis of rotation chosen, okay, here. That's half of the distance D, 1.5 over 2. That's how we got 0.75 meter, okay. So on the other side, where we have the torque, clockwise torque that will be produced by the weight of the boy, okay, exerted on the plank. That small m is the mass we are looking for, and the corresponding lever arm is 2.25 meter. How did we get that? It's because the boy is his lever arm corresponds to L over 2 minus D over 2. And we already explained later, earlier, that L over 2, which is 3 minus D over 2, which is 0.75. So 3 minus 0.75, that's how we got 2.25. Okay, and as we continue with our, what do you call this, with our application of algebra, all right, we come up with the value of the mass, which is 30 kilograms. So you see, okay, using the principle of torque directly, okay, in this situation, we are able to calculate for the unknown mass of the boy. What does this mean? Okay, uh, this mass m is the maximum mass that any person, okay, should have if he attempts to, for example, start walking, okay, on the ramp. Say he starts at any point between the two supports, he walks towards the end, the far end, right end of the plank. All right. Okay, since we are assuming that if he reaches the far end of the plank, that is the point where he is on the verge of tilting the plank. All right. And so therefore, if the mass of a person is higher than 30 kilograms, okay, um, he won't be able to reach the end of the plank, okay, probably a little beyond this point, okay, where the right support is, a little beyond that. If the mass of a person is greater than 30 kilograms, okay, for example, if the mass of a person is 60 kilograms, he would just probably reach, okay, a distance, okay, half of this, Okay, this is 2.25, right? So he may not be able to go beyond 2.25 meters. Okay, if he does, or he attempts to exceed half of 2.25, then the lever, I mean the plank will already rotate. Okay, so that is the meaning of our answer, which is 30 kilogram. Okay, we are not saying that the person that has to walk, okay, on top of the plank has a certain specific mass. Okay, we are just saying that who is the right person, who is the right boy, who can walk from the middle of the plank supported by these two supports, somebody who could walk towards the end of the plank, okay, and reaches the end of the plank without tilting the plank. And that's exactly, okay, is equal to a mass of 30 kilograms. Okay, so that ends our tutorial. Thank you very much.